Listomania. Like a rat, oh, not easily offended. I don't let it go. From the mass to the masses. Listomania. Oh. What? Oh, you know what? Because I'm dumb. Okay. Like a rat, oh. I feel like there's got to be a way I can adjust the white balance. All right. So today is about all right, we kind of have to bang through these sections because I'm pretty behind this week. Geometric concepts of length, distance, and perpendicularity, which are well known for R2 and R3, are defined here for Rn. These concepts provide powerful geometric tools for solving many applied problems, including the least squares problem mentioned above. They had an introduction thing. In order to find an approximate solution to an inconsistent system of equations that has no actual solution, a well-defined notion of nearness is needed. So that's sort of the context. All three notions of length, distance, and perpendicularity are defined. Okay, the inner product. If U and V are in Rn, we regard U and V as n by 1 matrices. The transpose of UT is a 1 by n, and the matrix product U transpose V is a scalar or a 1 by 1 matrix. UTV is called the inner product and is often written with a dot. The inner product mentioned in the exercises for 2.1 is also referred to as a dot product. Okay, so it's just what you think it is. It's the sum of the element-wise multiplication. Okay. We're not going to go through that example. That's pretty basic. Though this is nice. It shows that, okay, so inner products are commutative. They distribute over vector addition. They're associative with respect to scalar multiplication. And the inner product of something with itself is always greater than or equal to 0. And it's equal to 0 if and only if U is 0. And that makes sense. Because, like, you're summing up a bunch of squares. How could it possibly be 0 if the elements weren't all 0? Okay, properties B and C can be combined several times to produce the following rule. So you take a linear combination of like some basis, and you can take out you just apply this rule. Okay, so this is just another neat thing. So the length or norm of a vector V is defined by these two bars around it. It's like a double absolute value almost, but it's not. But it's the square root of the dot product with itself. Okay, here's another identity. To do this, compute the square a vector whose length is 1 is called a unit vector. If we divide a non-zero vector v by its length, we obtain a unit vector because the length of u the process for creating u from v is something called normalizing, and we say that u is in the same direction as v. Several examples that follow use the space-saving notation for column vectors. Okay. Find a unit vector. Okay, so that's fine. Let W be the subspace of R2 spanned by this vector. Find a unit vector Z that is a basis for W. Okay, pretty basic. Distance in Rn. We already know. We are now ready now to describe how close one vector is to another. Recall, if A and B are real numbers, the distance on the number line between A and B is the absolute value of A minus B. Two examples are shown. This definition of distance in R has a direct analog. For u and v in Rn, the distance between u and v, written as dist uv, is the length of the vector u minus v. That is the norm of u minus v. Okay. In R2 and R3, this definition of distance coincides with the usual formulas for the Euclidean distance between 2 points. Okay, that makes sense. Just look at this picture for a minute. Is that a well-defined operation, or is that like? I think the reason why it's not is if we just do rand 10. If we did this and then we did x, we would just do norm of x minus y, I think. Okay. The rest of the chapter depends on the fact of the concept of perpendicular lines in ordinary Euclidean geometry and has an analog in Rn. Consider R2 or R3 and two lines through the origin determined by vectors u and v. The two lines are perpendicular if and only if the distance from u to v Oh, yeah, that's interesting. From u to v is the same as the distance from u to minus v. This is the same as requiring the squares of the distances to be the same. Yeah, that's actually really cool. I never thought about that. Okay, yeah. So then you end up with this cool thing that that the squared distances are equal uh, if and only if 2 u dot v is equal to minus 2 u dot v, which happens if and only if u dot v is equal to 0. This calculation shows that when vectors u and v are identified with geometric points, the corresponding lines through the points in the origin are perpendicular if and only if the dot product is 0. The following definition generalizes to Rn this notion of perpendicularity. Observe that two vectors u and v in Rn are orthogonal to each other if u dot v is equal to 0. Observe that the 0 vector is orthogonal to every vector. The next theorem provides a useful fact about orthogonal vectors. The proof follows immediately from the calculation in 1, which was what? Okay. The right triangle shown in figure 6 provides a visualization of the lengths that appear in the theorem. Two vectors u and v are orthogonal if and only if orthogonal complements. To provide practice using inner products, we introduce a concept here that will be of use in section 6.3 and elsewhere in the chapter. If a vector z is orthogonal to every vector in a subspace W of Rn, then z is said to be orthogonal to W, the subspace. The set of all vectors z that are orthogonal to W is called the orthogonal complement of W and is denoted W perpendicular. I don't know how read as W perpendicular or W perp. Bro, I'm on that W perp. That shit's W. All right. Let W be a plane through the origin in R3, and let L be the line through the origin and perpendicular to W. If Z and W is in W, then the line, if Z and W are non-zero, L is on, or Z is on L, and W is in W, then the line segment from 0 to Z is perpendicular to the line segment from... Okay, yeah, that seems obvious. To the line segment from 0 to W. That is, the dot product is 0. Okay, so each vector on L is orthogonal to every W in W. In fact, L consists of all vectors that are orthogonal to the W's in W. Consists of all vectors that are orthogonal to the W's in W And W consists of all vectors that are orthogonal to the Z's in L. That is, L is equal to W perp, and W is equal to L perp. Bro, L perp, W perp? Come on, they picked the perfect names for that. They really handed me that. They said, bro, we got you that L perp. Nah, I'm just kidding. We got you that W perp. All right. The following two facts about W perp with W a subspace of Rn are needed later in the chapter. Proofs are suggested in exercises. Okay, a vector x is in W perp if and only if x is orthogonal to every vector in a set that spans W. Okay, so if you have a basis, why not just say that? Why not just say it's orthogonal to every vector in the basis? Why not just say that? Maybe this is somewhat more general, but whatever. W perp is a subspace. The next theorem and exercises verify the claims made in section 4.5 concerning the subspaces shown in figure 8. What do you think about this? The row space of A is orthogonal to the null space. Okay, this theorem seems interesting, but what does this arrow mean? A. But in the column space of A, it's crazy that you can select that text. The column, how do they make these diagrams, dude? That's actually cool. The column space of A is orthogonal to the null space of A transpose. Okay, we need to work. We'll do the exercises because I don't understand that. A common way to prove that two sets S and T are equal is to show that S is a subset of T and T is a subset of S. The proof of the next theorem shows that the null space of A is equal to rho A perp. It is established by showing that null A is a subset of rho A perp and rho A perp is a subset of null A. That is, an arbitrary element X in the null space is shown to be in the row space the rho A perp. And then an arbitrary element X in rho A perp is shown to be in the null space. Okay, here's the theorem. Let A be an m by n matrix. The orthogonal complement of the row space of A is the null space of A. And the orthogonal complement of the column space is the null space of A transpose. The row column rule for computing AX shows that if X is in the null space, then X is orthogonal to each. Wait, hold on. Oh, that is true. That is true. Because basically the row Oh, that's interesting. Okay, this is the best sentence. The row column rule for computing AX shows that if X is in the null space, then X is orthogonal to each row, because you're taking, when you do the matrix multiplication, matrix vector multiplication, you're doing a bunch of dot products. Bro, there's like a family of crows that have just been born. And they just hang out here all day. I have my noise canceling on, so you probably can't even hear it, but it's quite okay. Since the rows of A span the row space, X is orthogonal to row A. Conversely, if X is orthogonal to row A, then X is certainly orthogonal to each row of A, and hence AX equal to 0. This proves the first statement of the theorem. Since this statement is true for any matrix, it is true for A transpose, thus the... Yeah, okay, cool. That's actually a really easy proof. Optional, angles in R2 and R3. If U and V are non-zero vectors in either R2 or R3, then there's a nice connection between their inner product and the angle. What character is that? I don't even know what character that is. What? It's so weird. PDFs encode this stuff so poorly. All right. Between the two line segments from the origin to the points identified with U and V. The formula is U dot V is equal to the norm of U times the norm of V cos whatever. So to find the angle, then what do you do? You just divide by this. You get U dot V over norm U, norm V, and then you get cos theta. And then you take arc cos or whatever. A cos. A cos D. The verification for R3 is similar. But is it true? How do you get the angle between arbitrary vectors in Rn? Okay, so why did they not say that? If this formula generalized to Rn, I don't know why they didn't say that. Okay, so these practice problems, so let's just do this. I'm just gonna okay, so I think we just use A, B, right? Oh. Okay, so we get that. So now we get and we can actually simplify this to be norm A. Okay. So this is first, or I don't know, foo. Then we get AB over times A. So now what we've done is we've scaled it. I don't actually know what this does. What does this do? What is this quantity? What is see, I read this whole thing and I don't understand geometrically what the dot product represents. Because like dot AB, I understand that there's zero if they're orthogonal to each other. Think of a dot product U dot V as measuring how much of U points in the direction of V. Drop a perpendicular Okay. Sort of. It's the projection. All right. All right, so we did problem one. Um, all right, find a unit vector U in the direction of C. So I think it's just going to be C divided by norm C, right? Oops. Then if we do the norm of this, it's 1. Bam. All right, show that D is orthogonal to C. 5, 6, minus 1, dot CD. Okay, this is like pretty close to 0. Use the results of A and B to explain why D must be orthogonal to the unit vector U. Because orthogonality does not care about the magnitude of the vectors. It just cares about their direction. We'll see how they answer that, but that's how I'm going to answer that. Let W be a subspace of Rn. Exercise 38 establishes that W perp is also a subspace of Rn. Prove that the dimension of W plus the dimension of W perp equals Rn. But we know that the null... Hold on. This is a good one. Let's just think of R2 for right now. Prove that one thing we'll say is that orthogonality guarantees linear independence. So all right, let's see how they answered it. Okay, all this is nonsense. But what did they say for this part? Yeah. Okay, that's easy. All right, if W is not the zero subspace, then you take a basis that's less than or equal to n. Then this is a good proof actually. Okay, so I'll write this one down. So if we have W subspace of Rn, then dim W plus dim W perp is equal to n. So the proof is let A be the P by n row, or P by n matrix, having rows Okay, so first off, we'll just say the dimension of W is P. So you take P1, you take B1 to BP basis of W. Then form A, which is P by N. First, we got to just remember some basic stuff about our rank theorems and stuff like that. So if B is some arbitrary m by n matrix, then you have to remember that the image, that the vectors of the image are in Rm. Right? If we take like A is equal to rand 2 by 4, then the kernel has elements in R4. So X in ker A x in R4. Okay, so then y in MA, y in R2. So so if we just did A times rand 4, we get a 2-element vector. Okay, so now I kind of get what A is. So A is equal to has rows of B1 transpose BP transpose, where each BP is in R, an element of Rn. Okay, cool. Yeah, so that's right. It follows that W is the row space of A. Yes. Clearly, W is equal to row of A. Theorem 3 implies that by theorem 3, W perp is equal to wait, let's see. Yeah. Okay, so we're here right now. So dim W perp is equal to dim null A. Thus, so dim W plus dim W perp is equal to the see, this is where I get confused. The row space is the rank? I thought it was the column space. I think that this is in this section. 4.5. We should probably review that. But we constructed A, so that's fine. We constructed A to be that. Dim row A. plus, and then this is going to be the dim of W perp, dim null A, which is equal to the rank of A plus the nullity. Okay. All right, we can read through these exercises, but I'm hoping to get done with these ones pretty quickly today. Compute the quantities. I don't know if we need to do that. Find a unit vector. I don't know if we need to do that. Find the distance between that. The dist this is going to be the norm of A minus B, right? So then we don't need to do that because you just remember the definition. Determine which pairs of vectors are orthogonal. No, we can skip those. Okay, true, false are good. So just go through these. 19. So this is section 6.1. V dot V is equal to the norm of V squared. Yeah, that's true. This is also true. If the distance from U to V equals the distance from U to minus V, then U and V are orthogonal. That's true. This is also true, right? Yes, this is true. That's just the Pythagorean theorem. 24. If vectors V1 to VP span a subspace W, and if X is orthogonal to each Vj, then X is in the W perp. That's also true. If X is orthogonal to every vector in a subspace W, then X is in W perp. That's also true. That's true. Is there some sneaky stuff they just got by me? This is false, because you need to take the abs val of C. 26. For any scalar C, is that true? If we unwrap it, we get like we get like 1, 2 dot, let's say it's minus 1 times 3, 4. This is a dot. Then we get 1, 2 dot minus 3 minus 4, which is equal to minus 3 plus minus 8 which is equal to minus 11. Now, if we pull out the minus 1, I think that's true. Is that in the theorems, though? Oh, yeah, it's in the theorem. Okay, 27. For a square matrix A, the vectors in col A are orthogonal. The vectors in the column space are orthogonal to the vectors in null. Ooh. The rank is the dimension of the column space. The rank of an m by n matrix A is the number of pivot columns. And the nullity of A is the number of free variables. Where do they introduce row space? Did they already do that? Okay, there. I think that this is false. Yeah, I didn't think so. No. Yeah, they're different subspaces. That's what I thought. So then I'm going to say that this is false. Vectors in the column space of A are not orthogonal. Okay, 28. For an m by n matrix A, the vectors in the null space of A are orthogonal to vectors in the row space of A. That is true. That's true. Okay. Okay, true, 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 false, true, false, true. Nice. Okay, we got them all. That was easy. We don't need to do that one. You just think of them as matrices, and I think it works out. Let U equal U1, U2, U3. Explain why it has to be. Okay, this is obvious. I mean, it's like, think about squaring all the elements of that list. It's like, if any of them are negative, they become positive, and then you sum them up. It's got to be greater than or equal to 0. And, it's only the case that they're all 0 that the norm is 0. Plus, I mean, not that it's like a good justification, but it's like, okay, if you're a mathematician and you want to define the length of some vector, how long it is, surely the only thing that should have 0 length is the 0 vector. So the definition sort of matches your intuition in that instance. Let U be this, we compare and contrast U dot V, U squared, compute and compare. I don't want to do that. Verify the parallelogram law. What is this saying? The norm of U plus V plus the norm of U minus V. So what are they saying? They're saying the norm of U plus V squared plus the norm of U minus V squared is equal to 2 times the norm of U squared plus 2 times the norm of V squared. Okay, let's get on the just gonna move this over. Okay, so this is the geometric picture. Now, the norm of U plus V is going to be the length of this, and then you're going to get the length of this. In the case they're orthogonal, we're going to have So yeah, so u plus v squared is equal to u squared plus v squared. But so then we're gonna get. So then we would get, if we sum these up, we'd get u plus v squared plus u v squared is equal to. But surely the norm. Surely the norm. Surely v is equal to minus v. Norm v is equal to norm minus v. So then we get 2. But I think there's a logical gap here, because you can't just do this. In the case that they're orthogonal, it's fine, because these identities hold. So these rely on ortho. So you can't just do that. So you need kind of a different strategy to prove it in the non-orthogonal case. Oh yeah, there you go. Okay. So that's what we want to do. So we have uh, we're going to just take u minus v. And what is this equal to? This is equal to the dist uv squared. And dist of ab is equal to square root of I think it's A minus B dot A minus B. Okay, so then this is going to be equal to U minus V dot U minus V. Now to expand that out, we are allowed to FOIL it, right? So this is going to be equal to U squared plus V squared minus 2 U dot V. So that's nice. So now if we do U plus V squared, this is effectively equal to the dist of U and minus V. So then we're going to get is equal to U plus V dot U plus V, which is going to be equal to U squared plus V squared plus 2U dot V. And then these two cancel. And then you're just left with what we had. Okay, so we just did the parallelogram law. Next problem. Okay, let V equal to AB. Describe the set of vectors x, y that are orthogonal. For the first case, it's everything is orthogonal. It was already in the text that that's the case. But the second one, I don't really know what they're going for. Because it's like if A and B is 1, 1, then 1 minus 1 is going to be orthogonal to it. So I don't know what they're really going for. Oh, that's a good way to do it. Okay, so let's write that down. So for problem 33, it's going to be yeah, it's the span, because you can scale this by any amount, it'll still be orthogonal. So that's like the general form. Okay, that makes sense. Let W be the set of all X such that so W is like U perp effectively, or the perpendicular of the span of U. So imagine we have some line in space. Then you're going to get a plane through the origin of all the vectors that are orthogonal. I don't know. Describe W in geometric language. I don't know about that. Or I don't know about the theorem. Oh, that's smart. Yeah, treat the transformation as of U. So it's just going to be the null space of U, right? Yeah, the kernel. I always get kernel and image mixed up for some reason. All right. Suppose a vector y is orthogonal to U and V. Show that y is orthogonal to U plus V. Oh, interesting. Oh, this is actually really easy. We can do this one in like 1 second. Okay. 35. "36. Suppose y is orthogonal to u and v. Show that y is orthogonal to every w." Yeah, you just take out the linear combination. That one's so easy. Let w equal the span of p vectors. Show that x is orthogonal to each. Then x is orthogonal to every vector in w. Yeah, it's the extension of this to an arbitrary number of vectors. It's still obvious though. You just take out the scalars, and then once you have the dot products you know are zero because you're because x is orthogonal to each element of your basis, so then those dot products go to zero. And then you get a sum of zeros. Let W be a subspace of Rn. Okay, 38 may be good. I'm gonna get a coffee though. I'll be back. All right, last problem of the section. Let W be a subspace of Rn. Let W perp be the set of all vectors orthogonal to W. Show that W perp is a subspace. Okay, so to show something as a subspace, first we need to show 0 is in it. So to show that 0 is in the set of vectors orthogonal, or is a vector that is orthogonal to all vectors in W, we just note that the dot product with 0 is always 0, or the dot product with the 0 vector is always 0. But the next thing you need to do is you need to show that it's closed under scalar multiplication. So let's take some arbitrary vector in W perp. What do we know? We know that by definition, it is orthogonal to every vector in W. Or by construction, rather. So then, if we so first off, it's an element of the set, and it satisfies the constraint. Now we multiply it by an arbitrary scalar k. Now, if what we want to do is we want to show that that element is also in W perp. So the way we do that is we take we basically I don't know, maybe this is a leap, but what we could do is we take a basis of W. God, I want these family of crows to move. All right, so we take, let's see, what did they recommend? But yeah, you take a basis of W, and then you just show that the scalar, that the let's say k times x is in W perp because it's orthogonal to every element of the basis. Therefore, you could take an arbitrary linear combination of the basis of W, and that element is going to be orthogonal to x. So we just showed closure under scalar multiplication. Now we need to take two vectors, u and v, that are in W perp, and show that u plus v is in W perp. So if we have let's say that we have like B1 to BP basis of W. Want to show for u v in W perp that u plus v is in W perp. Now, if we can show that B1, or that u plus v dot B1, or rather bi, for some arbitrary I, well, we know that that it distributes, so that we know that this is going to be equal to u dot bi plus v dot bi, and these both go to 0. So then we've shown that u plus v is orthogonal to every basis element. So then you could take a linear combination of the basis element, which is equal to u, i.e., it's an arbitrary element of W, and it's going to be dotted with u plus v, it's going to be 0, so therefore it's orthogonal, therefore it's in W perp. Okay, so we just showed verbally that W perp is a subspace, which is great. I actually like that proof. I feel like I could really wrap my mind around that proof. All right, so that wraps it up for orthogonality, or inner product length and orthogonality. Now we're going to do orthogonal sets. Okay.